Welcome to this session of my presentation. Good morning, good afternoon, good evening, wherever you may be in this part of the world. And my presentation title is Generator Protection. My name is John Kweku Amo Otu, and I've been a professional electrical engineer for about 30 years, and I'm based in the United States. Okay, so this generator protection presentation is actually total number of slides is about getting close to about 600. So I've broken it into several different sessions. So this session will focus on the first session of generator protection. So there's going to be about 10 of these sessions that I'll make a presentation on generator protection. So this session is going to comprised of I'll talk about generator and its components as you see it in a typical power plant, and I'll also talk about ANSI nomenclature for generator protected relay. As you know, protected relay engineers basically speak in numbers. Our jargon is based on numbers. So if protected relay engineer says 87, definitely you know what he's talking about. He's talking about differential protection. So we'll talk about ANSI designated nomenclature that is basically designated for generator protection elements. Then we'll talk about pictures. Basically, I'll show you pictures of typical faults that we see in generator windings. Then we'll talk about typical generator connections that we see in power plants and industrial facilities. Then finally, for this session, we'll talk about different grounding schemes that we have for generators. Okay, so this slide shows you a typical picture of a small-sized based generator. So as you can see over here, you have a small-sized generator with a generator enclosure. And this duct shows you where air passes through to cool the stator winding. Then on this side is the rotor. So basically, the rotor basically carries the magnetic field. And the magnetic field it's what basically induces voltage into the stator. So on this rotor, basically, it's the extension part. So this is a small-sized generator on itself that helps to generate the DC voltage that is fed to this rotor. Next is another picture that shows you a bigger size picture that shows you the rotor that has been taken out of the generator stator. So as you can see over here, the rotor windings are embedded in slots in this region of the rotor, and basically this is basically the mechanical shaft that is coupled to the turbine shaft. And this is the end ring area, and cooling is also achieved through ducts on the various sections of this axial length of the rotor. This is a much bigger picture of basically a larger generator. Actually, this generator is rated at 650 megawatts. As you can see, this is a big generator. So as you can see, these are the turbine sections. As you can see, these are all the turbine piping basically that allows steam to be able to go to different sections of the turbine. So you can have the high pressure section here, intermediate pressure section here, and the low pressure section here. So basically the high pressure steam, basically that's part of the steam, the content, has it's about, I would say, about 90% dry steam, and very flowing at a very high pressure. So that is why they call this area high pressure section of the turbines. So the turbine blades on this side basically are much smaller in size. So as you progress to the intermediate section, the turbine blades are basically increased in size. Then on the low pressure section, basically the turbine blades are much larger. So on this side is basically where the generator is located. So the generator is located at the farthest end. Next is another picture from a different angle of the same generator, 650 megawatts generator. So as you can see, and much closer, these are the different sections of the turbine. So the mechanical power is basically generated in this section. So you have the steam that is flowing through various sections of this part of the turbine, basically to generate the mechanical power. And the shaft of this turbine is coupled to the shaft of the generator rotor, and basically the mechanical torque is developed, and it converts to electrical torque. And so that is what drives the generator to generate electricity at the output of the generator. Next, it's other component of the generator that I showed to you in the previous slide. Okay, so remember, I showed you that we have a rotor. Basically, a generator consists of a stator and a rotor, right? So the rotor is the rotating piece of the generator. The stator is the stationary piece, right? Okay, so the rotor, as I indicated, is fed with a DC voltage and current from an extension system. So as you can see over here, this is a starter excited system of extension. So that is where the DC voltage and the DC current is fed through these brushes. So you have a slip ring here, and you have these brushes. So that is what feeds the voltage and the current. Basically, it feeds the voltage, and as a result, current is generated and is fed to the winding of the rotor to create the magnetic field. So that is what creates the revolving magnetic field, and the revolving magnetic field, as it rotates, it's able to cut the stator winding, and that is how it induces voltage into the stator winding. Next, we'll talk about ANSI nomenclature. Like I indicated, that protective relay engineers speak in jargons in terms of utilizing numbers to talk to each other. So we'll go through the ANSI designated numbers that we use for generator protection. So ANSI device number 40, right, is loss of field. Okay, so loss of field is, let's say you have a magnetic field that is set up on the rotor winding. So if you lose the extension system, basically the setup of the magnetic field is going to change. So that's how this relay ANSI device 40 detects a fault due to extension system by changing impedance based on the setup of the magnetic field on the rotor. Next is ANSI device 64F, and that is a field ground on the rotor. Okay, let's say if there's a turn-to-turn short on the rotor, it is this relay that detects the fault, 64F. Next is phase distance relay, and that is ANSI device 21. If you have an external fault, let's say in the system, in the AC grid, right, and this ANSI device relay 21 is basically a backup relay for the generator differential protection. So the amount of contribution from the generator towards that AC grid fault, external fault, is detected by this phase distance relay. So as you can see over here, this is also based on impedance. It's an impedance-based relay. So it utilizes CTs and VTs, voltage elements, to basically calculate, the impedance. And also, it is made in such a way that it sees basically, it's more directional. Basically, it's pointing towards the generator as well. Next, it's ANSI device 24, and that's volts per hertz, right? So if a protective relay engineer says that, okay, ANSI device 24, definitely, I know it's a volts per hertz relay. So what this relay does is basically, its goal is basically to determine an overexcitation condition. And how does an overexcitation condition occur? It occurs, let's say, if you have a problem with the excitation system, and basically, it leads to higher voltage, at a generator terminal. Or let's say you have a loss of sensing of voltage through instrumentation, and also you have a load rejection on the grid. from other generators, so that can cause basically over voltage condition. And also, we have a frequency element in it. It's a V over F. So the V stands for voltage over frequency. So for frequency, if you have a heavily loaded generator, you can have in the AC grid here, you can have a drop in frequency, and that can affect the volts per hertz setting as well. Next is ANSI device 60FL. So that is fuse loss, right? Okay, so basically, you have VTs that are basically installed at the terminal of the generator. And basically what this VT is to basically sense the voltage measuring parameters of the generator. So on the high side of the VTs, you have fuses that basically protect the VTs. So if you basically have a fuse failure, right, then basically this relay is going to sense that unbalance of voltage and basically affect its output to trip the generator. Next is 50 BF and 50 N. Okay, so this instantaneous element. So like I indicated, protected relays talk about numbers. So 50 BF means instantaneous breaker failure, and 50 N is instantaneous neutral measuring element. So these this relay basically, if let's say there's a breaker failure, let's say if a relay sets an output and it's supposed to trip the unit breaker and it fails, right? Then after a period of time, that is when this relay senses that if there is still current flowing through the breaker, and from there it starts time to activate to basically trip other breakers that are in close proximity to the unit breaker that is supposedly to be tripped. Next is 27TN, and 27TN is basically the 10 harmonica relay, under voltage 10 harmonic. 27 means it is an under voltage relay. So what it does is this relay is utilized to complement high impedance grounding relay 59J or 59N that is located basically detects ground faults at the stator. So because the 59J relay or 59N relay can only detect ground faults all the way up to about 95% of from the generator terminals all the way up to the neutral. So the remaining 5% is not protected. The 59G or 59N relay cannot detect ground faults on the remaining 5%. So we utilize the 10 harmonica neutral under voltage to complement and basically cover the remaining 5%. Next is 87G. When the protected relay talks about 87G, he's talking about generator differential protection, right? Specifically for the generator. So basically this type of protection scheme has basically CTs are the terminals of the generator and CTs are the neutral of the generator. Basically what it's doing is basically measuring the differential in current based on Kirchhoff's law. That is what comes in, the same current must come out. So if there's any difference, an appreciable difference based on a minimal threshold, then basically that indicates an internal fault. Then we have 87U. Okay, so when do we utilize 87U relay? 87U relay is utilized when basically you are protecting a combination of the generator and the step-up transformer. So 87 differential relay excuse me, protects both the generator and the step-up transformer. Next is 59. 59 means an overvoltage relay. So you can utilize 59 for each phase that you protect. Next is over and under frequency. So you can have these are frequency elements that basically protect the turbine side of the turbine generator. So basically 81O is over frequency protection, and 81U is under frequency. That is we have a threshold of under frequency set point that the turbine is supposed to operate, and beyond that basically then that is when the 81 under frequency element relay kicks in. Then likewise, for over frequency, we also have a threshold, and these thresholds are basically provided by the manufacturer. There's a chart that the manufacturer provides that tells you the operating regions and the allowable frequency that you're supposed to have. And if you go beyond the time that you're supposed to operate before you take the generator out of line. Next is 32, and this is more of directional power. Let's say if you have a reverse power, you have a reverse power flow into the generator. And if you have a reverse power flow into the generator, then basically the generator basically converts from being a generator to a motor. So this is when this relay basically detects that reverse directional power flow. Then next is a 59N element. Like I indicated, we utilize the 59N or the 59 chain through a high impedance grounding scheme. For most of the large generators. Like an example being the 650 megawatts generator that I indicated. So we utilize basically a single phase distribution transformer at a neutral, install it at a neutral, and basically derive a neutral from there, and we utilize this relay that is connected across a resistor, and the resistor is sized based on the stray capacitance from the generator terminals. Next is a typical setup of the generator protection elements for a generator for a typical power plant. All right, so as you can see over here, this is the connected utility system. So the AC grid is on this side, right? Okay, so this is the unit breaker, and its ANSI nomenclature is 52. So anytime you use the word 52, then we know that you're talking about a breaker or a unit breaker. So this is the generator step-up transformer. This is what steps the voltage from the terminal voltage of the generator to a higher voltage. So let's say you have a typical generator that has an output voltage of 30.8 kV, right? And you step it up to 230 kV or 345 kV. This is basically implemented by this generator step-up transformer. It steps the voltage up from 30.8 kV to 230 kV or 345 kV based on the desired voltage that you need on the transmission end. Okay, so for the protection scheme of this generator step-up transformer, right, as you can see over here, we have a 51N element and a 50N. So this is an instantaneous neutral over current protection, and this one is a time of a neutral over current. So this basically acts instantaneously, and this one basically operates based on an inverse curve. Next is all these basically protection relays can be a multifunction digital relay, a microprocessor relay, right? Okay, so you can have all these protective element as a single relay. So we have the 81O, like I indicated. This is basically this relay basically operates based on over frequency of the generator. When the generator is basically, the turbine generator is operating on over frequency condition. And what is an over frequency condition? Let's say the generator has a nominal frequency, operating frequency, right? Like 60 hertz, right? Okay, so the manufacturer will allow you to go beyond that. Let's say 60.5 hertz or 61 hertz. Beyond that, then basically, operating beyond that is going to be timed, and after that, you're supposed to trade the generator. Similarly, for 81U, which is the frequency element, let's say if you have a 60 hertz nominal operating frequency of a generator, let's say the manufacturer is going to allow you a tolerable range of 58.5 hertz to 60 hertz. Beyond 58.5 hertz, definitely the manufacturer will put a timing in it and basically trip the generator offline. Next is 59, and this is an overvoltage element. And let's say if you have an overvoltage condition at the terminal of the generator, due to a load rejection or due to inappropriate operation of the extension system, basically, or due to inaccurate sensing of voltage, then this is the protective relay that will sense it. 24, it's volts per hertz, and basically it's measuring voltage and basically dividing it by the frequency, and its goal is to basically to prevent overextension of the generator and the generator step-up transformer, because overextension can cause saturation of the core of the generator and the transformer as well. Next is 50 BF, and like I indicated, 50 BF is a breaker failure element. Basically its goal is basically, let's say if this relay element is supposed to trip this unit breaker, right, and it fails to trip it, then that is when this relay senses current flow through this breaker. When it senses that current flow after a period of time, then it knows for sure that this breaker has not tripped. Then it's going to time out and basically activate other breakers that are in close proximity, especially breakers that are on the AC grid, to trip it, to prevent the flow of evolution and cascading of from current flow into the AC grid. Next is 60 FL, and that is fuse loss. So what it's doing is basically the fuse that is connected on the high side of the VT, located at the terminal of the generator. Basically, what it does is, when the fuse goes out, it detects that unbalance of voltage measurements. Next is a loss of extension, and this is impedance-based protector relay measurements, and basically it's based on the setup of magnetic field on the rotor, right? Okay, if let's say there is a fault on the rotor, or there's a fault somewhere in the stator, right? Basically, this relay detects the change in the magnetic field, and it detects the change in the magnetic field based on changing impedance, and it's able to trip the required breaker. Next is directional reverse power flow. Let's say if you have a reversal of power flow into the generator from the AC grid, right? Then this generator is going to basically convert from a generator to a motor, and you don't want that. Basically, it's going to cause heating and a failure of the generator. So that is when this relay detects that reversal of power flow from the AC grid. Next is ANSI device 21, and this is a distance protection. This relay basically acts as a backup to the main differential protection, and basically what it's looking is basically it detects the contribution of the generator contribution to a fault in the AC system. Next is 27. 27 is basically an under voltage relay. Let's say if you have heavily loaded generator, basically the voltage is going to go down, or inaccurate sensing of voltage, then this is when this relay sets in and basically trips the required breakers. Next is 27TN. This is a 10 harmonic under voltage relay, and it complements 59N. Like I made mention that 59N stated ground fault relay is made to see only 95% of the stator winding, right? So the remaining 5%, this relay does not see and does not cover that region. So we need another relay to complement that protection. So that is when the 27TN complements the remaining 5%. Matter of fact, they set it in such a way that it overlaps. It covers about the last 10% of the neutral of the generator by creating an overlapping zone. Next is it's another multifunction digital relay type 1, and basically, so it all depends on how much cost you want to put into these microprocessor relays and the number of elements that you're going to have. So this is a type 1, this is a type 2, and type 1, these are all the elements that it has, and the type 2, these are the elements that it has. So the next element is 87G. This is the differential protection. This is the main protection system for the generator, right? So basically, you have CTs at the terminal of the generator and CTs at the neutral of the generator. So basically, it's measuring the difference in current. Next is 64F, and this is basically the rotor field ground relay that detects faults on the rotor winding, and if there's a 10-to-10 short, on the rotor or field winding failure, this relay is the one that basically detects and trips. And I made mention about high impedance grounding, right? This is the single phase distribution transformer that is utilized to achieve the high impedance grounding. Basically, what it does is it limits the ground fault current to about 5 to 20 amps, to prevent damage into the stator winding and the stator core. Next, we'll still talk about ANSI device numbers. So this basically shows you, all the applicable relay elements that form the generator protection, right? Okay, so I made mention of distance relay, ANSI device 21, force per hertz, ANSI device 24, and sync check, ANSI device 25. We utilize that sync check. Let's say if we bring in the generator, up to speed, so once it reaches its desired voltage, right? We'll measure, the voltage coming out of the generator and the phase angle, right? And we also measure the AC grid voltage and phase angle. So if it comes within a certain range, if both the voltage and the phase angle comes within a certain criteria, then we close the unit breaker. So this is how we utilize this relay basically to close the unit breaker and integrate the generator to the AC grid. Next is under voltage elements, and that's device 27. Then directional power relay, I made mention, for reversal of power flow into the generator. Then a field relay, loss of excitation, so basically if you have, a field that's set up on the rotor winding, and basically you lose that magnetic field due to a problem with your excitation system or inaccurate measuring system, or let's say you have a VT failure, then that is when basically your magnetic field is going to change, and that's how this relay detects a problem with the excitation system and a problem with the rotor winding. Next is the field breaker. The field itself that provides DC voltage and current has a breaker that basically, it closes in to basically provide the required voltage and current to the rotor winding. Next is negative sequence relay, right? Basically, it's let's say if you have a phase unbalance, and phase reversal, ANSI device 46. So this is what this relay does. It detects that amount of unbalance. So for each generator, the manufacturer specifies the allowable unbalance that is supposed to achieve for a period of time, right? So let's say a negative sequence unbalance, let's say 5%, 6%, 10%, let's say for a certain period. So I squared T, and it also provides a K, and the K number is basically a multiplier that is provided by the manufacturer. Next is instantaneous overcurrent. Basically, this is usually a backup for the main differential protection. And this is usually utilized in smaller generators, where there's no need to basically have a main protection scheme utilizing a differential protection. Next, it's time overcurrent relay ANSI device 51. So this basically has much more timing. It's not instantaneous and operates on an inverse current. Basically, it basically protects the generator based on overloading and onset of fault. Next is AC circuit breaker. So that's ANSI device 52. Then we have 52A, 52AA. Those are auxiliary contacts for the breakers. So for breakers that use high-speed contacts, basically we utilize 52AA and 52BB. Next is over voltage, and that's ANSI device 59. And for voltage unbalance due to a fuse loss, that's ANSI device 60. Then for ground for detection, we utilize 64. Then for frequency element protection, we utilize 81, ANSI device 81. Then lockout relay. Lockout relay is ANSI device 86. Okay, so depending on the owner of this generating plants, right? Okay, so the owner can come up with a scheme, that basically from the output of this relay elements, I don't want to go straight to the breaker, into the breaker. I want to go through a lockout relay, right? So the lockout relay is the intermediary from between the relay and the breaker, right? So the lockout relay also is, has a multiplying contact, has a lot of, multiple contacts, that it trips other elements. So let's say you have a differential protection that sets in, right? It basically activates. Then that differential relay, it's basically wired to a lockout relay, right? So the lockout relay trips has a lot of contacts, right? It trips the unit breaker. Then it trips the turbine side valves, right? Steam valves. Then it trips the field breaker. So basically, what a lockout relay does is basically has that multiplying contact to trip other sources that are supposed to be tripped in addition to tripping the unit breaker. Next is differential protection, and I made mention that is ANSI device 87. Next is a beautiful picture that shows you a damage to a stator due to a ground fault on the stator. As you can see over here, it's a big core damage, right? There's a damage in the core and basically a winding damage as well. So this is not pretty. So that's why you need all those expensive protection scheme to protect your generator. Another damage, but it's time to the end bell area, end winding area. As you can see over here, these are the coils that come out of the end winding area and are formed in a Robel configuration. They call it a Robel, the way it is wound. So this is the end winding area, and that's where the fault occurred. Now let's talk about typical connections of the generator to the bus or the utility, right? So this is a direct connector. Typically, this has a low impedance. These are utilized in industrial, commercial facilities, and they are very simple, very inexpensive. Okay, so you can also have different grounding schemes on different generators. Let's say at an industrial facility or commercial facilities, you can have, let's say, 2 or 3 generators, and you can have one generator connected in high impedance, right? You can have one generator connected in low impedance, and you can have one generator connected in solidly grounded system, right? And no grounding in that part, on the neutral part, right? And you can have them all connected to a common bus, right? So these are usually used in industrial, commercial, and facilities. And basically, you can have problems of circulating current because of the different grounding scheme. So it is very appropriate that you have a single grounded scheme in such a connection. Then we'll talk about unit connections, and this is what is utilized by most of the generation facilities, generating plants. Basically, it's called unit connection, and it has a high impedance, as you can see over here. This is the neutral of the generator, right? And it's connected to this high impedance single phase distribution transformer. Basically, that sets up a high impedance path to ground. Then it goes to a step-up transformer through a unit breaker. So it has a dedicated transformer to it. This is a generator step-up transformer, and it has a dedicated grounding scheme that it has. These are mostly, like I indicated, utilized in utility power plants, and also for very large industrial facilities. And this is what is utilized. And it provides, I'll say, about 95% seated ground fault protection, and you can utilize for the remaining 5%. I made mention that you can have a complementary protection by utilizing the 2017 third harmonic undervoltage relay. Next, you can have multiple high impedance connected generator to a bus and to the AC grid, where basically they are all connected through a single step-up transformer, right? Basically, you are saving costs through that, and also these are used in very large industrial and utility system, And for this one, since you have a similar grounding scheme, high impedance grounding scheme, there's no issue of circulating current. If you were supposed to have a high impedance grounding here and a low impedance grounding here, that is when there's the possibility of circulating currents. Now let's talk about the types of generators that we have over here, out there in the world. Okay, so we have cylindrical rotor synchronous generators. These generators are very fast. Let's say your most common that I've seen is 3600 RPM. They rotate at a faster rate. And we have a salient pole. And, salient pole synchronous generators are much slower. That is what is used in hydro power plants. But for gas turbine plants and oil plants, and coal power plants, this is basically most of them utilize cylindrical rotor and a steam turbine plants. They utilize a cylindrical rotor. And some also utilize an induction generator. We have induction generators utilized in wind farms. So this is a nice picture of a cylindrical rotor and stator generator. As you can see over here, basically, this is someone doing an inspection, performing an inspection of the state of core and the state of winding during an outage, right? As you can see over here, the rotor has been removed, right? So I used to do these inspections, many decades ago, when I was working at the Exelon and Emerald. Yeah, so basically, what is the person is doing is, this is basically, about 1 month outage that, usually they take, so there's a major outage. For them to take the rotor out of the generator, that means like it's a major outage, So you have the generator engineer, or maybe the plant engineer, that has been trained how to do these inspections, basically, doing his inspections. So basically moving from one end of the generator to the other end, basically inspecting each slot of the generator where the windings are located, and the end bell area where the end winding area, looking for heating and looking for damages to the core and to the winding and the insulation system. Next is a typical picture of a rotor, So as you can see over here, these are the rotor slots, right? This is where the windings go in. So the windings are embedded in these slots, as you go around the peripheral surface of the rotor. So basically you have this is a two-pole machine. You have a north and the south pole, magnetic pole, right? So the windings go into these slots all the way, and they are wound, basically, to basically achieve the required voltage that is supposed to, magnetic field that is supposed to create to induce that amount of magnetic field into the stator to create the required voltage. Next, it's a nice picture of a salient pole, rotor and stator, right? Okay, so I told you that the salient pole type of generator is utilized in a hydro power plant, and because it has many poles, right? It could be 100 poles, 200 poles. The speed is slow, and basically that's what you need, for a hydro power plant that utilizes water, basically on the turbine side to basically create the required turbine energy to turn the rotor of this generator. Comparably to cylindrical rotor, basically has two poles, and two poles basically, has a very fast speed, like 3600 RPM. So now let's talk about the typical grounding schemes that we have for generators. I think I mentioned briefly about the types of grounding schemes that we have, when I was basically elaborating on the different connections of generators to different buses and to the AC grid. But now let's go deep dive into the different grounding schemes that we have. Okay, so we have an ungrounded scheme. Basically, if you have a delta scheme, it's ungrounded, or you can have a Y that is not, it's floating, it's not grounded. You can have a solidly grounded system. You can have a low impedance grounded scheme, medium impedance grounding scheme, and a high impedance grounding scheme. But most often than not, we have these ungrounded scheme, solidly grounded, low impedance, and high impedance. It's a medium impedance. Basically, in the US, it's not popular. It's mostly popular in the Europe and the Asia region. So, as the name sounds for itself, basically, you have there's no connection for an ungrounded scheme. There's no connection between the neutral and ground of the generator. So basically, the neutral is floating. So because of that, you have an embedded, inherent phase-to-ground capacitance, from the generator and the transformer winding, and basically, that helps to limit, high impedance ground faults to very, very low values. So it's very difficult because of the, the ungrounded nature, to detect ground fault is very difficult. So you have to come up with a scheme to derive grounding detection for this. So a phase to ground faults are basically results in the shifting of the neutral. And the unfaulted phase is basically see much more of a face-to-face voltage. Okay, so next is a reactance grounded scheme. So basically we are utilizing a reactance to limit the amount of current, ground fault current. So for a solidly grounded generator, right? As the name says, basically we don't have any resistance or reactance in between the neutral and the ground, right? Okay, so basically, the ground, if a ground fault should occur, it is only the generator impedance that limits the ground fault. So because there's no zero sequence impedance, the ground fault can be very large indeed, because there's nothing on the neutral to limit the ground fault. So basically this can cause a lot of damage to the generator, especially for large generators. So most often than not, solid grounded generators are utilized for very small generators, very small generators, non-critical generators. Next is a high impedance grounding scheme. So I've already made mention that we utilize a single phase distribution transformer at the neutral of the generator. And basically it goes through tens ratio to basically limit the fault current between 5 amps to 20 amps, typically about 15 amps. Next is a typical picture of a low impedance grounded scheme. As you can see over here, our goal is basically to limit the ground fault to 400 amps. So that 400 amps should be good for enough for this generator in an industrial facility. Next is another picture of high impedance grounding scheme. So as you can see over here, this is the single phase distribution transformer, right? So on the secondary side is a resistor that basically is connected across the secondary winding of this distribution transformer. So across that is your 59 G or 59M relay, ground over voltage relay. So basically it's detecting over voltage condition across this resistor to determine a ground fault condition in the generator. Next is we can also have a hybrid impedance grounding scheme that utilizes low impedance grounding scheme, a combination of a low impedance grounding scheme and a high impedance grounding scheme. So when the generator is in operation, right, it is connected. You have a vacuum switch over here, right? Basically, so the generator is grounded through this low impedance grounding scheme. When there's a fault, right, the 87 differential relay detects that fault and basically trips this breaker quickly and basically opens the switch so that the generator can be grounded through this high impedance part to limit the current flow into the generator. Now let's talk about fault classification in generators. We can talk about internal faults and abnormal operating conditions in the generator. Okay, so for internal faults, we can have face-to-face or line-to-line faults in the generator. We can also have face-to-ground faults. We can have double face-to-ground faults. We can have three-phase voltage faults, and we can have roto-ground faults. And all these are basically, a lot of them is due to insulation failure, core damage, and also deterioration of the insulation with time, right? And this can be attributed to mechanical vibration, environmental conditions, and also external conditions from lightning that can cause those damages. Then we also have abnormal operating conditions, that is over voltage, under voltage, over fluxing, over excitation. Then we can have over frequency, under frequency, loss of excitation, inadvertent energization. Inadvertent energization basically occurs, let's say, you have an outage, right? And you have a generator that has been disconnected from the grid, and the generator is on a turning gear. That is, you have when usually during a minor outage, right? When the generator is not, the generator rotor is not taken out, and the rotor is put on a turning gear, so it turns very slowly. Because what it is the rotor is so massive and it is warm, right? So if you don't continuously put it on turning gear and turn it slowly, well, basically the rotor is going to bow. It's going to start bowing and shake, and basically can create a vibration problem. So that is when the rotor is put on 10 gear. So if you have, let's say, an operator, that goes into the switchyard and, inadvertently, closes, the generator breaker, basically what is going to happen? The generator is going to be energized, and there's going to be a backflow of reverse power, right? And it's going to motorize the generator. So inadvertent energization, anytime there's an outage, right? Be it minor or major, this relay is energized, to basically protect the generator from accidental energization. And basically it operates based on 50 and 27 relay combination. That is instantaneous current and under voltage condition. Because when you energize the generator, the voltage is going to be very low. It takes a little bit of time for the voltage to build up, right? Okay, but the current is going to be high. Once you energize, the current is going to be high. So it measures that and basically determine that we have an inadvertent energization. And basically what it's going to do is basically trip any breakers that are supposed to be tripped. Then we have a loss of prime motoring, and that is when you have reverse power, right? 32 basically flows into and basically motors the generator. Then out of step condition, that is answer device 78, right? Okay, so if you have a generator that is, as you can see over, the AC grid has many transmission lines that are interconnected. So you have, let's say, thousands of generators, or modify that. Let's be realistic. We have about, let's say, 200 of generators that are all interconnected to many transmission network, right? Okay, so if you have a generator, right, that has a fault that basically cascades, and that generator is not able to recover, and basically the fault is not able to uh, be isolated, and basically the generator, isolated from the rest of the generators, right? Basically, there's something they call out of step, right? The generator is going to lose synchronism with the rest of the generators. So that is when the out of step relay comes into play, right? To be able to finally trip the generator, and if any other generators that might be affected, basically it trips it. Next is overload condition. Let's say that is based on 51, and blown fuse for the VT, and open fuse for the VT. And winding thermal protection is, let's say, if you have excessive heating in the winding, be it in the stator winding or the rotor winding. So now let's talk about which sections of the generator turbine that all these protection schemes and abnormal schemes that I've talked about. Okay, so for reverse power and frequency, it applies to the turbine. So that is why these turbine manufacturers gives you a chart, that basically shows you all the operating allowable frequencies that you're supposed to have, and if you go beyond that, how long you're supposed to have that. And also reverse power applies to the turbine. That's when the turbine steam valves are basically shut off, closed, to prevent basically the turbine from spinning based on a reverse power, and the generator is moving at that instant. So negative sequence unbalance applies to the generator, right? The loss of oxidation applies to the winding, the rotor winding. Then pole slipping also applies to the rotor winding. Then rotor ground fault applies to the rotor. Then a thermal overload on the rotor applies to the rotor. Then for the stator, we have a differential, right? That we can have overall and generator differential. Then over voltage applies to the stator. Then overfluxing applies to the stator. Then thermal overload of the stator applies to the stator. Then also voltage restraint, and step distance, applies to the stator. Then stator ground fault applies to the stator. Then accidental energization, that is inadvertent energization during outage, applies to the stator. Good morning, good afternoon, good evening, wherever you may be in this part of the world. Welcome to the second session of my presentation on generator protection. And basically, the first thing is we'll give a refresher on what was presented during the first session. And during the first session, basically, I basically discussed the different protection relay elements that we have for fault condition, and also the different protection relay elements that we have for abnormal conditions with the generator, and designated unseat device. Like I indicated in the first presentation, protection relay engineers usually utilizes numbers in their conversation. For instance, if a protection relay engineer is talking about 5051 and a basic element, then basically it's talking about instantaneous protection and time of protection. Then I did discuss and present the different connections that we have for generators, where we have direct connected, where the generators are directly connected to a bus, or unit connected when the generator is connected to a unit generator step-up transformer through a breaker. Then we have a different grounding schemes for generators that are discussed, and the different types of solidly grounded schemes, and which is basically utilizing commercial, applications and industrial applications. Then we have low impedance grounding scheme that is also utilizing commercial and industrial applications, where they basically, the ground fault current is limited to between 200 amps to about 400 amps, so that this prevents damage to the generator windings in the core. Then we also have, high impedance grounding scheme, and this is mostly applicable to larger industrial facilities and also bigger utility generating stations. And what it does is it utilizes single-phase distribution transformer that is connected to the neutral of the generator to limit the ground fault current between 5 amps to 25 amps. And it utilizes a resistor that is connected across the single-phase distribution transformer, and you have basically a 59GN relay that is connected across the resistor to be able to detect voltages and to provide when there's a ground fault. Then also is the hybrid impedance. The hybrid impedance usually is also utilized in larger utilities, where basically criticality comes into play. So this utilizes both low impedance and high impedance scheme, to basically form the hybrid. So when the generator is in operation, basically it utilizes a low impedance, when there's no fault. And when there's a fault, there's a 87 ground differential relay basically that trips a vacuum switch that is connected to the low impedance grounding scheme and also the unit breaker. Then it is able to connect to the hybrid impedance scheme during the fault to basically limit the ground fault current to 5 amps, between 5 amps to 25 amps. Next, on this presentation, basically, we'll focus mostly on instrument transformers. As you know, instrument transformers are dedicated for protective relays. Protection, it's current transformers, and basically that scales down the primary current to a secondary current of 1 amps or 5 amps. So as you know, the choice of 1 amp and 5 amps is utilized based on the location of the relay. If the relay is located much closer to the cities or further away. Then we have a voltage transformer, basically that scales down, the primary voltage to a lower voltage, line to line, about 120 volts, and line to neutral, about 69 volts. Then we'll also talk about how these instrument transformers are selected, so we'll talk about the saturation, how to basically calculate the saturation level of these CTs. So, in the previous session, like I indicated, the different abnormal operating conditions that we have for generators are over frequency conditions. So, and that is designated by ANSI device 810. So, over frequency conditions occurs most of the times, during load rejection. If you have a generator, basically that rejects a load, and basically, you have a loading on the network basically going down, and that results in an overfrequency condition. Overfrequency conditions are not much of a concern to the turbine side of the generator, but nonetheless, the manufacturers provide, curves and charts basically to show you the allowable, overfrequency range that and the timing, that you can achieve to operate during an overfrequency condition. A typical example is, if you have a generator that has a nominal frequency range of about 60 hertz. So you can basically, the generator manufacturer and the turbine manufacturer basically can tell you that, okay, I will allow an over frequency condition when you reach 61 or 60.5 hertz. Then that is when I'll put a timing place on how long you can go over 60.5 hertz. Next is under frequency condition. Under frequency condition is designated by ANSI device 81U. And under frequency condition occurs basically if you have an extensive amount of load picked by the AC network. The generator basically picking the load as well. So basically, as load increases, you have a frequency going down. Then also, you can have that escalation of changing frequency if there's a fault on the AC network, which basically can result in under frequency condition. So that is why some of the utilities basically have a load shedding for under frequency condition, so that basically they can basically stabilize the generator connected to the AC network. Next is loss of excitation. Loss of excitation is designated by ANSI device 40. Right, and basically loss of excitation occurs when, let's say, you have a problem with the voltage regulator. As you know that the excitation system is the one that provides a DC voltage to the rotor winding to set up the magnetic field. And this magnetic field basically becomes the rotating magnetic field for the rotor, and basically goes into sync with the rotating magnetic field of the stator. So the rotating magnetic field basically cuts and induces the stator coil to induce voltage. So we can have a loss of excitation condition, like I indicated, if you have a voltage regulator problem. Let's say you have a field breaker, a failure, or basically a field breaker that trips. Or you can have an internal, power electronics problem with the excitation system. As such, when this happens, there's a change in the setup of the magnetic field, and this is basically sensed by the loss of excitation rate. Next is inadvertent energization. And I made mention that this usually occurs, during a major outage. If you have a major or minor outage where the generator is on turning gear, turning gear that basically the generator is allowed, the rotor is allowed to turn on the turning gear. And there's a dedicated motor that allows the rotor So that prevents the rotor from bowing, because the rotor itself is hot. And if you allow the rotor to just be standstill, basically, it's going to bow, and basically it can result in vibration problems. So what happens is, if during a major or minor outage, if an operator, let's say inadvertently, closes, energizes the breaker in the switchgear, so basically it's going to lead to 3 to 4 per unit amount of current, right? If you have basically a strong grid, and also your voltage level will experience another voltage condition. So a combination of the 50 and the 27 element will help you to basically detect an inadvertent energization condition. If you utilize only 50 element, that is instantaneous element, no way that you'll be able to detect this inadvertent energization. But you have to use a combination of 50 element and 27 element. Next, we move on to the loss of prime mover or reverse power, and how does that condition occur? Let's say you have a steam turbine, basically that's integrated, to a generator, right? And all of a sudden you lose the prime mover, through, let's say, loss of steam. So then basically, the turbine side is out of the picture. Basically the generator will act as a motor and start absorbing active power from the grid, AC grid. So we have this relays basically that is able to detect the flow of power in the reverse direction, and prevents the generator from motoring. Because if the generator is motors for a long period of time, basically it's going to cause heating of the winding and both the stator and the rotor, and basically can result in failure of the generator. Next is out of step condition, and that is designated by ANSI device 78. Okay. So, like I indicated, in my first session presentation, you have about, let's say, about 20 to 50 generators, that are all operating and basically providing active power and reactive power to a system of a transmission network. So that is what they call a network, right? Okay, so if you have, let's say, a generator that basically loses synchronism, due to a fault that is not basically isolated as much as possible, then basically that generator is going to go out of, it's going to slip a pole, they call it slipping the pole, and it's going to go out of synchronism. And once it goes out of synchronism, the other generators are going to mimic what this generator that basically slipped the pole and going out of synchronism, they're going to mimic its behavior, and basically it can lead to a cascading and a widespread of power loss. So basically what this protected relay element does is basically it detects that condition and basically trips that the generator offline. It also has basically elements that they call them blinders, that basically allows basically prevents, let's say, if you have an increase in load, right? What it does is the impedance path of the load is going to traverse, it's going to move into the impedance diagram, the mode circle of the out of step condition. So basically, once it basically the load impedance hits this blinders, it's going to time how long basically this impedance trajectory is going to go into the circle and come out, because a typical fault, if it goes into the circle, is to continue to move into the circle, but a normal swing will go into the circle and come out quickly. So basically, you have blinders that determine the timing of these elements and block basically the tripping of this relay from that. It distinguishes it from actual out of step condition and just a stable power swing. Next is an overload condition. Let's say you have a generator that basically picks up additional load. Then basically you have this protection scheme that is going to protect the generator from that overload. Next is voltage transformer, fuse loss, and that is determined by basically designated by ANSI device 60. So you have VTs that are basically most of the times are located at the terminals of the generator that basically measures the terminal voltage and basically scales it down to 120 volts or line to line, or line to neutral of 69 volts. Right? Okay, so on the primary side of what this voltage transformer it has fuses. It has fuses both on the primary side and on the secondary side. So the fuses on the primary side basically can go out, and now basically when that condition occurs, basically it's going to lead to an unbalanced voltage condition. So when that unbalanced voltage condition occurs, that is when this relay element protects the generator. Next is winding thermal protection. As you know, you have the rotor winding, the stator winding, and embedded in the stator windings are RTDs. Basically that measures the temperature buildup of the stator windings. So basically, if the temperature buildup, let's say a typical example how such a condition occurs, if you have water cooled generators stator, and basically you lose cooling to the winding, and basically the winding temperature is going to creep up. So basically you have RTDs there, basically that determines the rise in temperature. On the other hand, if you have a rotor winding, and basically you have a temperature shock or cold shock, basically it's going to lead to a rise in temperature, and the winding temperature protection for the rotor is going to detect this condition. Next, we'll talk about the different types of generator protection for faults, actual faults. We did talk in the previous slide about abnormal conditions that can occur when the generator is in operation, but now we're talking about faults. So first is differential protection. This is basically the primary protection for generators. We're talking about 5 megawatts and above. And basically this is what basically is utilized as and it's very sensitive and basically selective. Basically it's able to distinguish it between an in-zone fault and an external fault. Next is state overcurrent protection. This basically becomes a backup for the differential. Let's say if for whatever reason the differential protection let's say gets saturated, CTs are saturated, right, due to an external fault, and the CTs are not demagnetized to remove that saturation. And let's say when the generator gets back in operation, there's another fault, and the differential protection fails to basically detect a fault, then basically the faults start evolving into a higher magnitude, a peak magnitude fault, and that is when the state overcurrent protection, the 5051, steps in to detect the fault and isolate the generator offline. Next is a negative sequence protection, and that is designated by ANSI device 46. This occurs basically if you have reverse, let's say a generator rotation is counterclockwise, then all of a sudden you have a switching phases. A becomes B, B becomes A, then basically it rotates in the clockwise direction. Then that is when basically it results in second harmonic frequency current on basically is induced into the rotor from the stator into the rotor, and basically this flows on the peripheral surface of the rotor, and through skin effect basically creates a heating in the winding and also the metallic components of the rotor. And as such, the manufacturers basically have a designated amount of negative sequence that each generator and type can handle, and that is based on the negative sequence magnitude and the time duration that in place that the negative sequence current is allowed to flow. So basically, the manufacturers provide a constant K for each generator. So I squared I2, I2 current, that is the negative sequence current squared times T, it should be equal to K. So that's how you set this relay. Next is reverse power, and I think I did make mention of that in the previous slide. And that itself, you can achieve a sequential tripping with that, where basically, 32-1, basically allows alarming, and 32-2 basically allows a tripping. So basically, when that condition, you move into the second level of tripping, basically that's when you trip all the steam valves, and also trip the field extension system, and trip the unit breaker. Next is 51V, voltage control of voltage restraint over current, right? Okay, so this is basically utilized for industrial type of generators, and basically in place of differential scheme, sometimes incorporating differential scheme can be expensive. So most of these industrial generators that are of lower magnetic MVA, they utilize that with 51V. The 51V element allows you, let's say, if you have a fault condition, right? Definitely, your voltage level is going to decrease. So there's a decrement curve that you're supposed to follow. And also sometimes, when a fault occurs, especially high impedance faults, the fault current magnitude is going to be so low that it will be difficult for the conventional 87G relay and 5051 relay to detect those faults. So that is how this relay is able to basically follow the decrement curve and basically identify a fault condition when there is a low amount of fault current below the nominal rate, even below the nominal rating of the generator. So basically, a low voltage and a lower current below the nominal voltage. That is when this protective relay element comes into play to detect the fault and isolate the generator. Next is overfluxing, and that is also due to load rejection or failure of the extension system, failed plug and failed breaker, failure, or voltage regulator failure, so that itself can lead to overfluxing. Or let's say, if the step-up transformer is lightly loaded, current and light load, you can have an overfluxing condition. So basically, it utilizes the voltage and the frequency. So you can have an overvoltage condition and a lower frequency, the frequency decrement. Then that is when this protector relay is able to detect that condition. And basically, it protects both the generator and the step-up transformer in combination to basically implement that protection scheme. Next is high impedance ground, and basically it's basically stator ground, and it's 59G, and that utilizes a grounding transformer, and basically that protects 95% of the generator stator. So the remaining 5%, is not protected. And basically we have to come up with a complementary protection scheme that is a third harmonic on the voltage scheme. So that is the 27-3TN, and that is implemented to protect the remaining 5%. Matter of fact, it's an overlapping is achieved so that it protects up to 5 to 10%. So it creates an overlapping scheme. Right? This is based utilizing the third harmonic is based on the philosophy, or basically each generator has an inherent third harmonic feature based on the way the slots of the core are made. So basically, actually the generator is in operation based on the loading of the generator. Different third harmonic voltages are built. So that's how the generator stator ground is able to utilize this scheme in addition to the 59G to provide 100% stator ground for the voltage. You can also, achieve 100% generator ground fault, and most of these schemes utilizing the nuclear complex where you have a harmonic current injection, 64S elements, and basically, you inject 25 hertz current into the stator, and then you measure the corresponding voltage. So based on that, basically you are able to identify a ground fault condition. So this is basically an online condition, and periodically, it injects harmonic current, and basically is able to determine whether ground fault has occurred. Next is the 51N. 51N element, neutral element, time of current neutral element becomes basically can be utilized as a backup power for the 59G. Let's say if your 59G fails to protect, then basically you utilize that. And also it can be used as the main grounding scheme, for industrial facilities, the neutral of the generator. Next is 5051N, and this is also utilized for low or medium impedance grounding generators, and this is mostly for industrial facilities. And next is rotor ground fault and 64F element. And this mostly it utilizes a current injection scheme, because the rotor winding and the rotor itself is floating, it's not grounded, so Utilizing current injection scheme, it is able to detect turnitin faults or faults of the rotor. Next is 87O. 87O is an overall differential protection. Let's say, in addition to the generator differential protection 87G, and let's say the utility, based on, investment, wants to invest more in protection, wants to add an additional zone of protection. So basically, combine both the generator and the main step-up transformer to provide to achieve an overall differential protection. So that gives us 87 volt. Next is under and over voltage protection. Under voltage is basically 27 elements, and the generator itself can achieve another voltage condition. Let's say you have a problem with the extension system, and basically you have a problem with measuring the voltage at the generator terminals. Basically, or you have a problem with the flow breaker. These are basically causes that will cause the generator to go into another voltage and as well over voltage condition. That is the 59 elements. Then I did talk about the under and the frequency protection in the previous slide. Okay, so you can have different connections for the voltage transformers that are used as an input to the protective relays for these generators. Okay, so as you can see over here, we have a Y ground, Y ungrounded VT over here. So as you can see over here, on this side is the Y grounded, right? Okay, so on this side is Y grounded. So we are able to achieve a line-to-line voltage of 115 volts. And over here, line to ground voltage can also be calculated. So that is 14,400 voltage. So that gives us the line to ground voltage over here. Next is another configuration. This time you are trying to achieve a line to ground configuration. In the previous one, we are trying to achieve a line to line secondary connection. Depending on the configuration of some of these membrane instruments, and particularly you can either you need to achieve a line to neutral parameters or line to ground parameters. So this in the previous slide, what we were interested is a line to line parameters for the measuring instrument or particular relays. And on this one, it's basically a Y ground VT. So as you can see over here, Y ground, right? So that is 13,800 over root 3. So that gives us our line to ground voltage. Then on this side, we are able to achieve both a line to line voltage and line to ground. So as you can see over here, we have a line to ground voltage on the secondary side of 115 over root 3, that's 66.4 volts, and a line to line voltage of 150 volts. Okay, so the VT ratio, as you can see over here, is 14,440 over 120. That is, they utilize the maximum voltage, not the nominal operating voltage, over 120 to achieve the ratio. So the ratio is 40,400 over 120, and that gives us a ratio of 120. Next, we'll talk about the different voltage classes, and also the basic insulation level that we have for these VTs. Okay, so for voltage class 0.6, this is the basic insulation level that it's supposed to have, and basically this protects the insulation elements of these instruments and the VTs. So for a voltage class of 34.5, right, we're looking at the BIL, basic impulse level, that is based on basically switching or lighting of 200 kV. And for a voltage class of 25, we're looking at 150 kV. Then a voltage class of 50 kV, 110 kV. Voltage class of 8.7, then we're looking at 75 kV. Then 5 kV is 60, and 600 volts is 17 kV. So basically, in the selection of your VTs, right, you pay much attention to your operating voltage and the voltage class that you are going to utilize. Next, for a current transformer, how do you basically size a current transformer? So basically, you have, let's say you have a 125 MVA transformer, right? Or generator, the generator that is rated at 125 MVA. Okay, so for the primary current, right, it's 125 MVA over root 3 times 30.8 kVA. Right? Okay, so that itself gives us primary nominal operating current of the generator, that is 5,230 amps. Right? Okay, so if you have a CT, right? Okay, so how do you size the CT, right? Okay, so the CT should be able to accommodate some overload, right? So you multiply 5,230 times 1.25 or 1.2. That itself allows you to incorporate some overloading into, so that the CTs can handle, let's say, if there's an overload in the generator. Okay, so that itself, 5,230 times 1.25 gets us much closer to us to select a CT rating of 8,005. Right, so the CT ratio is 8,005, that's 1600. So how do you determine the corresponding secondary nominal current? Right, we have a primary nominal current of 5,230 amps. So we divide 5,230 amps over 1600, and that gives us a secondary current of 3.27. Right, for a CT that has a primary current rating of 8,000 amps and a secondary current rating of 5 amps. Okay, so now let's talk about the different types of CTs that we have. I think we have the Bushing type, and also we have the bar type, right? Okay, or the split port type. So, and basically, this is an example of a picture of the bar type, right? Okay, so this is the primary conductor, right? Okay, so the primary conductor basically goes to a core that is inside, and on the core is wound secondary winding that has many turns, right? Okay, so the primary conductor is just a single bar or single turn. On the other hand, the secondary winding has many turns. So this is also an example internally how this looks like. Okay, so internally, as you can see over here, this is the annular core, and the secondary winding. It's basically this shows you the secondary winding wound many times, and the primary conductor is what you see over here. Okay, so next is the bushing type of CTs. Remember, I made mention that there are different types of CTs, right? We have the bushing, we have the bar type, and we have the split core type. And now we have the zero sequence CTs. The zero sequence CTs basically, encloses, let's say, the conductor or the cables. All, let's say if you have a three-phase cable, right? All three cables go through the annular core of this CT for the zero sequence type of CT. Okay, so for the bushing type of CTs, if let's say you have a circuit breaker, right, inside this part of the CT, the breaker bushing, right, this is where the bushing type CTs are located, right. So you have the CTs that you are utilizing either for protection and also for metering. They are located. And same applies to transformers, right? Inside the transformer bushing, inside a little bit up, below the main tank, they call that place, the turret. That is where the bushing type of CTs are located, and you either utilize them for protective relaying or metering. Next is the basics of current transformer, right? Okay, so basically, this shows you a cut view of how current transformer in the core. So basically, you have you apply voltage and current, and basically voltage, and basically it creates a current flow, and basically from the current flow you have the magnetic flux that flows through the core, and the magnetic flux links the secondary winding, and basically creates a corresponding induced voltage on the secondary side. Next is determining the turns ratio of this instrument's transformers, be it current transformer or voltage transformer. Right. Okay. So for a current transformer, right? Okay, the turns ratio is the primary current over the secondary current. Okay, so if you have a primary current of 100 amps and a secondary current of 5 amps, right? Okay, so that tells you a CT ratio of 100:5 or 20:1. Next is polarity. For CTs, polarity is very important. It tells you the direction of current into the equipment, and basically, how current flows out. So as you can see over here, for the primary side, that tells you the dot tells you the polarity that is current flowing into, and for the secondary side, for current flowing out, the direction of current flowing out. So primary current flows into the polarity, and secondary current flows out of the polarity. Okay, so for CTs, definitely you need to understand the equivalent circuit. So the equivalent circuit, basically, this is basically transposing or moving the magnetization branch from the primary side onto the secondary side. Okay, so you have this part is basically the magnetization branch, and this side is the secondary resistance and the secondary reactance. You can also have the primary resistance and the primary reactance. Right? Okay. Then this is the burden. Right? So the burden is basically the connected instrument transformer or the connected relay. That itself has a load. The burden is more of a load, and it is basically represented either by volt amperes or ohms. Okay, so like I indicated, the protected relays or the measuring instruments, are represented by bearings, standard. And there are standard bearings that are represented, shown given by ANSI standard C57. So if you have a burden designation, let's say you have a mirroring instrument, right, and basically it says that B.1, it means that the connected burden, the instrument, measuring instrument, has a burden, a load of 0.1 ohms. Similarly, 0.2, B, then 0.2 means 0.2 ohms. Then B 0.5, 0.5 ohms. B 0.9, 0.9 ohms. B 1.8, 1.8 ohms. Similarly, you can either choose either to designate your burden in ohms or volt amperes. Right? Okay. If you choose to represent it in volt amperes, this is how they are represented in volt amperes. To represent CT performance, right? CTs are represented by accuracy class. So let's say if you have a C100, what does C100 accuracy class represent? C200 accuracy class, C400 accuracy class, C800 accuracy class, right? Okay, so for C100, what it means that the maximum secondary side voltage that the CT can develop should be equal to 100 volts. More than 100 volts basically is going to go into saturation. For C200, that means that the maximum voltage that it can develop across the secondary winding is 200 volts. Then again, for C400, the maximum voltage is 400 volts across the secondary. And for C800, then again, 800 volts. Okay, so if you have a C100 accuracy class for CT, right? Okay, so, right, and it's supposed to have 20 times the amount of secondary, maximum amount of secondary current, right? You have a 5 amps CT, secondary CT, right? So 20 times 5 is 100. It means that we can only connect a measuring instrument or a protected relay that has a burden of 1 ohm. So 20 times 5 times 1, that gives us 100 volts. Now let's go to C200. Okay, so for C200, you have 20. Let's say you have a CT with a secondary amps of 5 amps, right? Okay, so 200. 20 times 5 is 100. So it means that to achieve the 200 volts maximum amount of voltage across the secondary, we need a 2 ohm burden to avoid saturation and to have an improved performance of the CT. Next is for C400, right? We have 20 times 5 20 times the maximum city secondary current is 5 amps. So 20 times 5, it means that the amount of burden that we need for a protected relay is 4 ohms. 20 times 5 times 4, that gives us 400. Right? Then 800 volts. Similarly, 20 times 5, so we need a burden of 8 ohms. We shouldn't go more than that. Other than that, we're going to have a problem with saturation and basically maloperation of the cities. So this is what I explained in the previous slide, right? Okay, so the relay accuracy, very, very important, especially for protection relays. Like I indicated that, with the terminal volts on the secondary side, basically what you want to achieve, let's say for a C100 accuracy class for a CT is 20 times rated. Rated is 5 amps, right? That's the rated amps for that CT. So 20 times 5 is 100. So to achieve 100 volts, maximum terminal volts, we shouldn't go more than 100 volts, right? We need only 1 ohm burden, right? So that's what it is. So the burden is the total ohms of the connected CTs plus the CT winding resistance plus the impedance of the leads all the way from the CT up to the connected protective relay. So that is a combination of how we calculate the burden, the 1 ohm impedance. So there's something they call a rated factor, right? So basically that allows the CT to carry overloading capability. And basically, let's say you have typical rating factors of 1.33. It means that the CT can carry overload of 33% more than its rating. Let's say if you have a CT of a primary current of 100 amps, it means that the CT can carry 133 amps on the primary side if the connected equipment is overloaded. Right? And it means that it should not exceed its temperature limits. Right? Okay, so this is basically the CT rating factor. And this is what is utilized to when you are selecting a CT, and basically to consider overload conditions. So if you select a CT with a rating factor of 1.5, it means that I can overload it 50% more. And basically, if you have 100 amps primary current, I can, you can basically operate it at 150 amps if the generator has to carry an additional load. Okay, so in sizing the CT, remember, I made mention, I think I've already talked briefly about all these factors that are considered in the CT sizing. Okay, so you should always consider overload. The first thing is consider overload, right? So you have expected load current, right? You have let's say 100 amps. You want to multiply it by 1.33, 1.5, 1.7. You consider that overload. So your CT sizing should be greater than that. So that allows you to overload, the generator that is basically connected to that particular CT. Next is saturation. Especially for external faults, right? When there's an external fault, you have that huge through fault current that goes through the generator. And basically, especially the X2 over R part, that basically based on other rotating equipment, especially this motors, the power plant, their contribution part. So that is what they call the DC offset. That basically allows saturation faster. So you should be able to size the CT primary, right, 20 times the primary current to be basically less than the maximum expected fault current. Let's say you have a maximum expected fault current of 60 kA, right? So you should be able to size it in such a way that 60 kA over 20, right, the CT wouldn't saturate. And there are IEEE Excel sheet for performing those calculations. So the CT primary, and that's what I made mention, is to size it in such a way that you avoid saturation. And also the insulation as well, should be sized well in terms of BIL, right? Selection of the right BIL. application to be able to coordinate with other equipment at a substation that has a similar delay. So that's what they call installation coordination. Okay, so CT saturation is dependent on a lot of factors, right? One of the factors is the turns ratio of the CT, and also the physical characteristics, size, core size, and saturation voltage. That's the C 100, C 200, the winding resistance, and the rating itself. And next is the connected burden, the lead resistance, and the relay itself, right? And, the current magnitude, the short circuit current magnitude, and the offset, which is basically detected by X over R. And the amount of residual flux that is in the CT core. So if you have a residual flux, remnant flux, they call it remnant flux in the CT, and basically you don't demagnetize it, then basically you are prone for that saturation, basically operating the CT too, because that extent of fault results in basically a higher fault current. Next is a CT saturation voltage, right? Okay, so basically you want to know the amount of error, right? 10% basically the goal. Let's say you have 10C100 CT. Okay, so what it's telling you is basically it should be able to develop secondary terminal voltage of C 400. Let's say a C400, 10 C400. It should be able to develop a secondary voltage less than 400 volts within a 10% error. It shouldn't have more than 10% error. Okay, so if you look at 10% error, so you find 10% of error, the amount of exciting current that could cause that amount of percentage error. Then you draw this line that should give you your maximum. So you compare this value that you are getting over here with what the accuracy class of CT that you have selected. Let's say C400 or C200 CT. In this instance, we are basically comparing it with a C200 CT, right? So let's say a 10 C200, it means that 10% of excitation current, right, should be somewhere here. Then I'll draw a line, and the voltage that I get over here should be less than 200 volts. So this is what they call the knee point voltage, right? Beyond this, that's the full saturation, and you don't want to operate in this region. We always want to operate in this linear region, right? And there are so many ways depending on the type of core, whether it's a gap core or non-gap core. Basically, there's something they call the tangent, basically that tells you the type of tangent you're supposed to utilize, either 30 degrees angle tangent or 45 degrees tangent. Next, it's burden, right? And I think I've explained what a burden is. And the burden is a combination of this is what the potential relay or the metering instrument presents, and this is the resistance of the leads that go to the potential relay or the metering instruments. Then, in addition, the internal resistance of the winding resistance of the CT. So you add all these up, and that gives you your burden. That's what is represented over here, right? The total burden is a combination of the internal winding resistance of the CT plus the resistance of the leads plus the impedance of the connector burden. And you always want to remember to basically convert the CT secondary resistance to 75 degrees Celsius. So this is an example of how you get the winding resistance of the CT, right, based on the CT ratio and the accuracy class. Next is remember I made mention that IEEE has a saturation tool, an Excel sheet that allows you, when you do your selection of city, and you select your city based on the accuracy class, right? And you have all the manufacturer's parameters for you to. So this Excel sheet helps you to determine if the city that you have selected will saturate or not saturate. If it's not going to saturate, you will have a very good performance as whatever protector really set it for. So basically, you have a rated RMS voltage that is supposed to achieve, right? Okay, so let's say this is a C200, right? Okay, so you can go a little bit up. It's 210 volts, right? Okay, so you have a test ratio of 200 volts. The winding resistance of the CT, the burden resistance, right? Okay, so the burden itself, it's presented as an impedance. An impedance consists of resistance plus the reactance, right? Okay, so the burden, the resistance of the burden and the reactance of the burden. That's what we have here. And then the system X over R ratio, right? Basically, that helps you on the DC offset contribution to the faulted point. Then the offset in the primary current, and basically that's talking about the DC offset part, whether you account for it or not account for it. Then if there's any remnants in the CT, right? Okay, let's say CT saturated before, and you did not magnetize it to remove that remnants. Then this is the maximum symmetrical fault current that you are expecting, and this is basically you do either manual calculations or system settings to determine the available short circuit in the zone that is being seen by the equipment. So based on that, you determine whether the CT that you have selected will saturate or not. Okay, so let's say you do your calculations, and let's say you find out that your CT will saturate, right, for some events. Then basically this is how you utilize microprocessor relays. Microprocessor relays have a lower burden compared to the conventional relays. Okay, so that will be another option for you. Or you can choose a higher turns ratio CT, or you can, in terms of performance class, you can also choose another higher accuracy class CT. Okay, let's say you chose C200, then you probably want to move to C400 accuracy class CT. So that itself, then you go back and plug in your parameters, and basically you will determine whether you're able to pass CT saturation. Next, this helps us basically to determine the voltage transformer ratings, right? Remind me that you have a basic impulse level that is based on lightning switching circuits, and basically select data based on your voltage class. Voltage class that you do insulation coordination to make sure that what you have selected is okay. Then now you have the ratio, which is basically the primary voltage, and also the frequency accuracy class disconnected. So this is a typical for BTs. You have an example of accuracy class, and basically this tells you the amount of error that you can achieve. So 0.3% error, that's what we want to achieve. 0.6 error, 0.12, 0.15. And basically, for mid-range class CTs, accuracy is very important. And you should be able to achieve accuracy at 10%, between 10% and to 90%. And sometimes it can even stretch below 10% to 5%. And sometimes it can even go beyond 100%. So for mirroring type of CTs, accuracy is much more important. And for protection CTs, it's more for saturation, to be able to mitigate saturation. Next is, this is a typical designation for an accuracy class for VT. So this basically tells you the error, and these tells you the different types of burdens that this VT can have. Yeah, with that, that comes to the end of my presentation. So listen to it. If you like it, select the like button with YouTube, and also subscribe to my channel. Thank you so much. So look forward to the next session, which will be the third session. It's going to be about 10 sessions because it's a lot of PowerPoint slides on just generative protection. And I decided to break it to make it easier for you to absorb the material, and also break it into smaller times. It helps watching it as well. Thank you.